Welcome to Brain Vision.
Today we're looking at gaseous hydrogen atoms, just initially in their ground state. If a free electron traveling with kinetic energy given to us as 12.75 electron volts collides with these hydrogen atoms, we want to know wavelengths of photons that we would expect to see. Just a quick recap of what's going on here. We know that these electrons can be excited into higher energy states, but it's not a spectrum. You must have X amount of energy to get to Y level. If you have less, you won't get there. It's quantized, it's steps. It's not just like a gradient. And to transition back from these excited states to lower states or eventually to the ground state, these electrons have to give off the energy, and that energy is given off as a photon, which we can describe the energy as just the Planck constant times their frequency, or just h times c, the speed of light, over their wavelength. And we want to know specifically for this scenario what wavelengths we would expect to see. So step one is just, what are the energy states possible? Recall that the nth energy level, E sub n, is described by negative, just because how these things are defined, z squared, z being the number of positive charges for the hydrogen atom. It's just the one proton. E to the fourth being the electron charge, m the mass, over 8 times the permittivity of free space squared, epsilon naught, and the Planck constant squared, h. All those constants just times a 1 over n squared relationship, which simplifies even further to just negative 13.6 electron volts times z squared over n squared. And for us, because we're doing hydrogen, z equals 1 always. So that's just a 1 over n squared. So pretty easy to calculate our energy steps. We just go ahead and plug in for n. So E1, our ground state, we know is negative 13.6 electron volts, just because 1 over 1 squared is 1. For the next state, E2, we have just negative 13.6 over 4, which is negative 3.4 electron volts. Similarly with E3, we're just dividing by 9, so it's just negative 1.51 electron volts. Similarly, we go on. E4 is 0.85. We're still negative here. Electron volts. And E5 is negative 0.54 electron volts. So note that while they're like decreasing in magnitude, they're all negative. So this is a much higher energy level than E1. So we want to look specifically at like how much energy it would take to go from one state to another, because as we know with these quantized energy steps, if you don't have enough, you can't go from one to the other. So going from E1 to E2, how much energy does that take? And to do that, we just look at the difference in energy between the levels. That's how much energy you need to put in to raise an electron from the ground state to the second state. So from E1 to E2, it's just 10.2 electron volts. From the ground state to the third state would require 12.09 electrovolts. To go from the ground state to the fourth state would take 12.75 electron volts, and to go from E1 to E5 would take 13.06 electron volts. And if you recall, our free electron only has 12.75 electron volts, and E has to be, less than or greater than this. So we know we can't go to the fifth because we don't have 13.06 electron volts. Sorry, I accidentally scrolled there. But we know we can only raise these electrons up to the 4th energy level, no higher. So we need to look at just the wavelengths resultant from photons emitted from the transition from 4 down. So 4 to 3, 4 to 2, 4 to ground, 3 to 2, 3 to ground, and 2 to ground. So what are these wavelengths? We know HF is equal to the energy of the photon, and we know that the energy is equal to the energy from the difference in states En going to state En prime, where n is the higher state. So if we divide both sides of these equations by the Planck's constant and the speed of light, we should be able to get to 1 over lambda equals z squared, all of our constants again, e to the 4th times m over 8 times epsilon naught squared over, now it's h to the 3rd, and c. And again, this is times 1 over n prime squared minus 1 over n squared. Now, you may recognize this glut of constants as the Rydberg constant, which we know to be equal to just 1.097 times 10 to the 7th, and that's in inverse meters, which is like 1 over meters. So then we can simplify to just get the wavelength by inverting this whole thing. Lambda equals, I'm going to do the denominator first for spacing. It's r times n minus n prime times the quantity n prime plus n. That's all dividing just n squared times n prime squared. And we're going to want to multiply that by 10 to the 9th nanometers over meters, because it's just much nicer to have our wavelengths in nanometers than meters for coherency's sake. So now it's just kind of a plug and chug. So going from n equals 2 and n prime equals 1 from the second state to the ground state, we know that that wavelength is 121.5 nanometers. Going from n equals 3 back to the ground state, n prime equals 1. That's an n. We can see that wavelength is equal to 102.6 nanometers. Going from n equals 3 just down one state to n equals 2, we can see that wavelength is 656.3 nanometers. Note, I'm conserving 4 significant figures on all those because that's all we have from the Rydberg constant. The n's are all integers. Going from the 4th energy state down to the ground state, you can see that wavelength is 90. That's a 9. 7.23 nanometers, still conserving 4 sig figs. Then from n equals 4 down to the second state, you can see, you calculate that wavelength is 486.2 nanometers. And from n equals 4 down to n prime equals 3, that wavelength should be 1875 nanometers. Nanometers. So that's it. That's all the wavelengths. How do we know? Because we know that the electron is only having 12.75 electron volts, so we can't excite the ground state electron to anything higher than the 4th state, and these are all the transitions from the 4th state down, and these are our 6 wavelengths. That is it.